Okay, hi guys. We're going to do the review for Unit 6, which is over polynomials. So the whole concept of polynomials here is that we're going to be dealing with really linear factors is one of the big things. Our critical points is really, I guess, what we're going to deal with in most of these. And our critical points for these, if we talk about these, let me switch color here. We need to, one, look at the leading coefficient, right, which is going to give us positive or negative. We're going to look at the degree, which is going to tell us if it's even or odd, which is going to give us our arrows, right, because odd means that they go in opposite directions. Even means they go in the same directions. And this tells us if the right side is up or down, right? If it's positive, it goes up, and if it's negative, it goes down. So that kind of is the start, and that all of that gives us our end behavior. Okay, so that's a large piece of what we're doing with this. Be it that we're writing from a graph or writing to a graph, or if we're sketching to a graph. So that's kind of like there's a common theme. It's these critical points. So I'm going to kind of go through the rest of them real quick. Our linear factors, I know I'm using acronyms here, so hopefully you're listening. Our linear factors are going to give us our x-intercepts, our roots, zeros, all those terms apply. You'll see that noted many different ways in here. With those, we would sketch those down, and then we would check next our multiplicity. Now, our multiplicity is going to give us of our linear factors, right? So we look at the linear factor's degree, right? We look at the little degree of the linear factor. And that tells us if it's even, right, that it's going to be a bouncing zero, one way or the other. And if it's odd, it's going to be a crossing zero. And so together with end behavior and the multiplicity, you've got basically everything you need to go back and forth between the graph of or a sketch of a polynomial or write the function of it. There's only a couple other minor pieces that we may talk about, which is the y-intercepts, right? And if you're in factored form, make sure that you plug 0 in and solve. If you're in standard form, it's the c value. From there, we also probably want to mention relative max or min, also known as turning points. I'm going to use P there. And those are the wiggles in the middle. So we've talked about those, right? It can be more than one, but we know that it's one less than the degree. Okay, that's the maximum number ones that it can have. You won't always see all of them. That just depends on how the multiplicity goes. But that's one less than degree. So you look in there, and if you're looking at the turning points, you could say, oh, this one has a degree of 3 because I only see 2 turning points. That would be how you would use that. We also have to calculate those, so we'll talk about how to calculate those, where the actual point is on those through the TI-84. Because that's what you'll be able to use in your test. If you're using Desmos, it's super easy. Just click on the point and it's there. But for this one, we'll go over that on the calculator as well. So there's a quick overview. And you'll notice this time I didn't get all of the review done for you because I wanted to do this video quickly. So I'll go over a few certain ones, and then obviously you'll have time to ask the rest of the ones in class. And maybe a secondary video if there's a lot of questions on stuff. But I don't think that there will be for that. I think you guys are going to be pretty good. So let's take one look at one of these here. We'll start with number 1. It says find the zeros of each function. So when it says find the zeros, you're finding the x-intercepts. And we know that we're going to use the zero product property for this. And you should be comfortable with that term by now. What it means is if it's in factored form, which this one is, and this one's not. So these two just let you know you need to factor these. Okay, make sure that you factor those two first. But in factored form, you just take each one of these and you set it equal to 0. So there's that first x set equal to 0. I'm going to take x plus 4, set it equal to 0. I'm going to take x minus 3/8 and set it equal to 0. When you solve those, you get the intercepts. So I don't really need to show you that work. So if I write this, x equals, we've got an intercept at 0. That's the first one, check. The second one, I'm going to subtract 4 to the other side. I'm going to have a 0 at negative 4. And the last one, I'm going to add 3/8 to the other side, so I'm going to have one at positive 3/8. Okay, that's as simple as it is to find the zeros. This one didn't ask for any multiplicity. There was no multiplicity. This one would have a multiplicity of 2 if we were doing number 2. All right, so this is this question here is kind of a big, actually, no, it's not. This one here, number 7 is the big one. We'll talk about that. Write a polynomial in factored form with the given zeros. So this is kind of the exact reverse of what we were doing here. So this one we set equal to 0 and we solve for it, isolated x by itself. Right now we have these already set up so that x is isolated. This is essentially what this one looks like. If we set those are all the zeros, 0 at 1, at -2, and at 3. So we're going to unsolve these is what we're going to do here. And so to unsolve, we would move this 1 to the other side. So I'm going to subtract 1 from both sides. So what do I get? X minus 1 equals 0. You'll notice that that looks like the linear factor that we started with kind of up here. So that's one of them. So we're going to go ahead and it says right in the polynomial in factored form. Now there's missing pieces. This we make some assumptions based off our level right now. So we didn't find an a value, which is your coefficient, but we're not worried about that right now. This one's going to turn into x plus 2 is equal to 0. And this one's going to turn into x minus 3 is equal to 0. If we solve those, again, adding 3 to the other side there. So that is as basic as it is for writing this in factored form. It's actually just a quick unsolve. You don't need to take it any further than that. All right, so for number 7, they do give us a whole graph. They tell us the window just so you have an idea of how big these things are. You can look at the x, max, and min. You know that these are moving by a scale of 1. This one's from -100 to 200, but that's not that important. Really what we're looking for is pulling pieces of information off. If you're looking at the degree, this is something that most of you may ask is, how do we find the degree? Well, first thing I'm going to look at for this one to see if I can find the degree is the number of turning points. The number of turning points should be 1 less than the degree. So because I have 2, I'm thinking that the degree is 3 of this particular polynomial. I'm also going to look at the number of zeros. So I'm going to go ahead and write 3 there for now. I'm going to move it over. And we're going to look at the number of linear factors because that should be equal to, right? The number of linear factors should be equal to the actual degree. So I should see 3. I'm not guaranteed to see 3. I can see up to 3 if this is a degree of 3. And it seems to match. We're not going to give you any complicated ones, so this one seems to fit. So number of linear factors. These should, in all purposes, for most of the ones you do, match. They don't have to, but if it is one where you can see all the zeros, they will. If you can't see all the zeros, meaning that you have one with multiplicity that bounces, you may not see the zeros. So if this bounced like this and bounced again here, you may not see the zeros. So just keep that in mind. All right, let's jump down here. I think I've talked a little bit about this already. So zeros that cross the x-axis, those have that's actually written backwards, odd multiplicity or degree of 1. Yeah, you can't say 1 with a multiplicity of 1. You don't really say that. So it's either 1 or it has an odd multiplicity like 3, 5, 7, 9. Zeros that touch the x-axis should be even, have an even multiplicity. And every one that touches the axis has multiplicity because you start at 2, which means there's more than 1 there, and you go 2, 4, 6, 8. So that's how you identify those. And if you look at all 3 of these intercepts, I'm not going to do it for you, I'm going to leave a little bit for you to do, that those are all crossing. And there doesn't seem to be any touching in that particular problem. Now, the other thing that we do need to talk about is the total possible number of zeros. So possible number of zeros is should match the degree. Okay, but you might not see all of those, and that's what you're going to call real zeros. In this case, our real zeros and our total zeros match. But if we had one of these that bounced and the degree was higher, we might not see all of the zeros. I'll show you a little better example down below. All right, again, this is all set up for you. I'll actually finish this off for you. This is written the right way. Function goes to negative infinity to positive infinity. Those is how I told you that's how it would start, and you would just need to be comfortable with the rest. So you get to do that. That's just your end behavior here. Okay, I'll fill that little infinity sign in there. Real quick, I'll do this one with you as well. Maximum means that they are the largest and smallest points, the maximum and minimum. We're dealing with relative max and relative min, and you should be able to see those. Here's a relative min. It is the relatively lowest point because we know that that goes farther, and this is a relative max because we know that goes farther as well. So they do have both of those terms. All right, flipping down here, again, notice it says no calculator, so we're sketching with all the pieces, kind of everything that we just did above. So first thing we probably want to do is note the leading coefficient. And to get the leading coefficient, we really should probably find the leading term. How do you find the leading term? Well, you can multiply this all the way out, and you'll notice that that's a degree of 4. So really you're looking at something crazy, and I would highly suggest that you don't do this. You could if you're crazy and nuts, but I wouldn't do this. you'll notice that that piece right there is what that one's saying. Plus you have to multiply it by the binomial x minus 3, and you have to multiply it in x squared in there when you're done with all that. That's a lot of multiplication. But the little bit of a, I want to say cheat, or the quicker, easier way to do that is just to look at all the first terms of your linear factors and multiply those, assuming that you also account for any degrees. So this x, at some point when we multiply all those out, will become x to the fourth. So this is x to the fourth times another x here, right? So we're up to x to the fifth times this x squared here, because we add exponents, don't forget. So we're up to x to the seventh. So we just got our degree, which is 7. But the more important part is that it's odd. That's more what we're concerned with here. We don't actually need to know that it's 7. We just need to know that it's odd. And all of these values are positive, so our leading coefficient then, by looking at our leading term, is going to be positive. And those are the two pieces that we needed to know. So if it's positive, we know that the right side of the arrow goes up. And it's odd, we know that the other side has to go the other way. So now we've found our end behavior. Okay, let's go ahead and start graphing, because I really do enjoy graphing as I go, so I can kind of see it come together. So if I start that graph there, I can have a down arrow on the left and an up arrow on the right based off my end behavior. Next, I need to go back and get my linear factors. So I need my intercepts. So my intercepts then are going to come from setting x squared equal to 0, x minus 3 equal to 0, and x plus 6 equal to 0. And you say, what about your degree? Well, we'll worry about the degree after. That's our multiplicity. So right now I don't need to be too concerned. What I find out, if I solve all those, I get a 0 at 0. That's what the x squared one comes from. I get a 0 at positive 3, and I get a 0 at negative 6. But this one has a multiplicity of 4. So I know that it's going to be a, well, let me change colors and maybe write it a little bit cleaner here for you. I'm going to circle this. So this one you find out has a multiplicity, is an even multiplicity. Right? So it's going to be a bouncing 0. Somewhat one way or the other. So let's label all these points then for these intercepts on the graph. So we know we've got one at 0, so there's my 0. I've got one at positive 3, and I've got one at negative 6. 1, 2, 3, 4, 5, 6. I might have to adjust my end behavior on this side. It's a little off, so I'm going to make it somewhere down in here. All right, so now we know that this is a, let me go back and grab a different color. This one was a bouncing, this one's a crossing, and this one is also a bouncing, because I forgot to mention that. That one's got a multiplicity of 2. Multiplicity of 2 for that one. I forgot to label that. So now that we've got that, let's go ahead and start marking these in. We know that 3 is a crossing for sure, so let's go ahead and cross that one. I'm going to guess that it's going to cross kind of like that somewhere or the other. So these next two are bouncing, and we have to make these end behaviors work. So the only way for this to bounce is if I bounce off of this side here. If I can't go through it, right, because my end behavior would mean that would make it a crossing, so it has to do that. So to intersect this one, and I didn't do a good job of this line here, so let's see if I can, they're usually nice and smooth, so I'm going to come up like that, and even, a little more symmetric usually, and this is going to bounce off of that one, and then that fits as the crossing, and then I can go up and through. So that's how I would sketch that. Again, end behavior, find your zeros, check your multiplicity, sketch it in. All right, jumping down here, I'm not going to do all of this because it's not too far from what we did, except for pulling the information off an actual graph. The ones that I did want to talk about a little bit was how many possible real zeros are there, and that's going to be based off the degree. So if we look at this function here, there's a turning point, there's a turning point. It's one, remember the turning point is one less than the actual degree. So right now I'm feeling like this is a degree of 3. Does it ask me that? Yep. Well, what is degree? Yeah, I'll help you out. It's saying that's a degree of 3. So let's check the zeros then. The zeros, right, should match the degree. I should see 3 zeros on here. And you're like, okay, Mr. Hallam, I only see 2 zeros, one here and one here. Well, let's be cautious. This one is a bouncing 0. So it means that it has to have some multiplicity. Right? And the minimum multiplicity, which we're going to guess, is going to be, it's got to be even, right? Because that's what it has a multiplicity, because it's bouncing, we'll say 2. So if this counts as 2, that counts as a crossing, we'll say it's 1. It could be a degree of 3. So our linear factors match our turning points in this case. We don't have any discrepancies. If you have discrepancies, then you got to go back and take a look and see, okay, what's going on here? So we do have a degree of 3. Which brings us back to the two questions that I kind of wanted to start with. How many possible real zeros are there? Well, if it's a degree of 3, possible. I think I wrote this is backwards. Sorry. So if it's the possible real zeros, it should match the degree. Okay, so in this case, there should be 3 possible real zeros. And then it says, how many zeros do you actually see? Well, how many do we see with our eye? We see 1, we see 2. We're not counting multiplicity, we're just seeing how many times it touches the x-axis. In this case, it's 2, because it's only touching 2. So there's 3 out there, because this one has multiplicity of 2. 1, 2, 3. But we only see 2. 1, 2 intercepts. Okay, so that question there, I don't know if we covered a lot in class. That's why I wanted to make sure that I covered this one, and I'll even do the one down here. Let's take a look at this one. It should be repeated, the same type of question. How many possible real zeros are there? How many real zeros are there? So let's see if we can do the degree first. So we're going to check our turning points. There's 1 turning point, 2 turning points, 3 turning points. So by the looks of it, it should be a degree of 4. So I'm going to sketch this in, and we may change it, but we're going to look at our zeros now and see if our zeros match a degree of 4. Well, this one bounces, so its minimum is a degree of 2. And this one bounces, so its minimum is a degree of 2. So that matches 4. So we're good with 4 then, because they seem to match up. So how many possible real zeros are there? Again, should match the degree, so we're going to say 4. How many real zeros are there? Meaning how many do we see? I only see 2. So hopefully you get the difference between that. All right. This one I'm going to run through one example all the way down, and then I'm going to be done with the review. So notice that this one says factor first because it's in standard form. These are going to be in factored form, so we're going to go ahead and do that. All right, so the leading coefficient again. Remember with the leading, I'll zoom in a little bit. So if we're using this polynomial, all we're going to do is fill out the information it's asking. Same stuff we've been doing. So to find the leading coefficient, we would take all the first terms and multiply them together. These both have a degree of 1, so it's really x times 2. Or the leading coefficient is 2x squared. Now, really what we want from that, this doesn't say it in the directions, but this is what I want you to do. What we want from that is that it's positive and even. Okay, that's what we're concerned with, because that gives us our end behavior, which we'll fill in right now. Our end behavior then says if it's positive, the right side goes up. If it's even, they both go up. Okay, that's what we want from the leading coefficient. Now, as for the degree, you saw how I multiplied those out. Add up the exponents, you can see I wrote it there, so we have a degree of 2. We can actually see it right there, 2. So the number of linear factors. Well, this 2 out in front, some kids are going to get confused by that. This is a solid 2. It is not a 2x, it's not an x. It's not a linear factor, it's just a coefficient. So don't think that that 2 is part of your linear factors. If it was an x, it would be. But in that terms, then we've only got 1 linear factor, 2 linear factors. So we only have 2 linear factors, which they should kind of match here, right? Our linear factors should match our degree. Number of turning points. Well, we're not going to sketch it first. We're just going to play off of how many our degree has. So a number of turning points for this should be 1, because it should be 1 less. Our y-intercept. Okay, this is another point where students may struggle a bit. I'm going to write over here. Hopefully you don't care. Now, if it's in factored form, you want to plug in 0 for your x value and solve for it. So that's what I'm going to do. Plug in 0 minus 1, 0 plus 3. So this is 3 times a negative 1 is negative 3 times 2 is negative 6. So my y-intercept should have a 0 for the x-coordinate and a negative 6 for the y. Okay, if it's in standard form, look ready. Boom, all done for you, negative 18. All right, so number of zeros, crossing. These are both odd degree. This is asking about multiplicity. So they're both odd degree. So we've got 2 crossing zeros. We could probably even label them. We'll say x equals positive 1 and negative 3. We've got 2. We've got no touching zeros. And so we have a total number of zeros of 2 and a possible of 2, which means that we're going to see all of the zeros. This one, again, we saw that on the last one. These may not match. If we have multiplicity, they should not match. All right, so the next part says calculate relative min and max. We'll do that in 2 seconds after we sketch our graph. We'll put it in the calculator, and I'll run through how to calculate it. All right, so let's sketch. So we're going to go back. Here are our zeros. We've got 2 crossing zeros at 1 and negative 3. Notice there's no scale, so we'll pretend. So there's 1, 2, 3. I'll change the color so we can see them stand out. There's 1 0. There's another 0. All right, they're both crossing zeros, but let's put our end behavior in first. Our end behavior, if we go back up, was up and up. So I'm going to put an up here, and I'm going to put an up here. And these are both crossing zeros right here. So when I come down to these, they have to cross. And this has to cross. So what do we set our y-intercept as -6? Let's see if we can make that fit a little bit. 1, 2, 3, 4, 5, 6. So I'm going to stretch this down a little bit, come back around. It's not perfect, but it's a pretty good job. And let's be honest, this is a degree of 2, right? So it should look like a quadratic. All right, so now let's put that into our TI-84 and see what that looks like. That's a repeat of it. Again, all I did was put the function into the y equals menu and I graphed. All right, now the tough part about this is that you may have to change the window to get that polynomial to look right. This one fit in a standard window. I'm not going to guarantee that every one you see will. So you might have to be able to adjust your x-min, x-max, y-min, y-max. You might have to play with that, but this one's good. So now what we're going to do is go ahead and calculate these, or this right here. I'll mark it over here. We're going to find this relative minimum. Okay, this turning point right there. It's a minimum because it's low. It actually is, and I should be a little more careful with this. Technically, this is a minimum. It isn't a relative because it happens to be quadratic. It is the lowest point. So just to be careful with my terminology there. So if we go back to this one, to calculate that spot on the calculator, we're going to get second calc. And then we're going to pick minimum or maximum. In this case, it's a minimum, so I'm going to hit enter. Now I want to find this point here. Left bound means be on the left of it. So I'm going to scoot to the left. I'm on the left. I'm going to hit enter. I'm going to scoot to the right. I'm going to hit enter. And it says guess. Don't worry about that. Hit enter again. So it tells me some awkward number, -1.000001. It rounds for this, so you're going to have to interpret the fact that that actually is a -1. It most likely could be a decimal. Probably a decimal more often than not. This one just happens to be neat. So it works out to be an actual value. So we found out that it was a -1. What was the other one there? -8, -1, -8. For my relative, or my minimum, not even a relative minimum. All right, so that covers everything that we're going to do. The rest of this is all the same down there as well. I think you have a pretty good overview of everything that you're going to be expected to do. Okay, so there's a review. If you have any more questions, make sure that you ask them in class.